Los Alamos National Laboratory and Scripps Institute of Oceanography. After staying in different institutes in Canada, USA, and Mexico, finally he decided to join Center for Atmospheric Science in 2011 as a faculty. He's working there. Currently, he participates with colleagues. I think we can see their names um, from other areas of Center of Atmospheric Science, which include but not limited to the hydrological cycle of the North American monsoon system, irrigation over the Iberian Peninsula, dynamical control of water vapor transport over Mexico with emphasis on synoptic large scale and mesoscale circulations. So please,
Thank you.
Arturo, it's all yours.
Thank you very much, and I thank Roy and for all his efforts to make this seminar workshop a real thing, and also the Institute of Geology and Geophysics. Today I want to talk to you about something a bit different from the stuff that you've been hearing lately, and this is more related to water, but water in the atmosphere and how it gets down to the surface. The common theme for all these colleagues of mine is the monsoon of North America, particularly David Adams, who has been working as an observational scientist in Sonora and Arizona. And he's with us. We are all four of us are here at Centro de Ciencias de la Atmósfera. And okay, so I'll be talking about two main things. The first is just to put in context what a monsoon is and how that phenomenon is part of the global atmospheric circulation system. And then I will talk later about the North American monsoon, which is the main topic of this talk. So this is an image that you get from the satellite. There is the global. I don't remember the acronym, but it's a new satellite, and it has a lot of resolution, horizontal resolution, about more or less around 10 kilometers, which is a lot for us. And you can get from the radar that it has on board. The backscatter will be proportional to the rain rate. So we have rain rates, which are very important. Just imagine that Mexico City has also oh, sorry, thank you. I hope not to, okay. Just imagine that in order to get rain rates in Mexico, we have a network of rain gauges, pluviometers we call them in Spanish, and those measure accumulated rain in a time period of hours. But these things can actually measure rain rates even at higher rates. The Institute of Engineering here has also another network with these drometers, which can actually give you rain rates of the order of millimeters per second. So these are very, very good things, but these are sensors at the surface. And this is a sensor on board the satellite. Okay, so what you're looking at here is a band, a rain band, across in the north of the equator. And it has several, the first thing you notice is that these rain bands are like organized in very large scale, planetary scale areas. So the one that is most striking is the one centered in India and in Eastern Asia. See, it's the Asian monsoon and the Indian monsoon here. So it has lots of rain here. And then you have the African monsoon also, which is located here. And then we have a tiny little one here, which is the North American monsoon, and it's our monsoon. It's really, Mexico is the core of the North American monsoon. And this line here is a control line. This magenta line is a control line for the water vapor. And the water vapor, integrated water vapor, is these shades of gray. Over here, what you see is the zonal average of these quantities of the rain rates. And in here, you see the curve that is smoother is the one that corresponds to climatology. And this is of this particular day. So you see, this is 27th of July, 2015, and yet it's not such, there is the departure from climatology is not so intense, it's not so big. So it's really a very strong signal here that we have for the monsoon. So the monsoon is part of the Hadley cells that give off their moisture when the moist air ascends in the vertical, and then in that ascent will give off its moisture as rain. Over here, what you see is the passes that the satellite goes from south to north. But the most interesting thing here is that this GPM is able to see the the electric discharges here from lightning. This is lightning. So it's very interesting. So it conforms to the places where the monsoon is located. And again, you have here the intensity of the reflectivity, which corresponds to the to lightning in this way. So you have a difference, small difference between ocean and land. This is just to give you a sense of how this thing evolves in time. Sorry. So in January, we have most of the rain belt located to the south. Here's the Amazon, so you have lots of rain here. The colors is rain rate per day, not rain rate per hour as you saw before. But this is in the south, and this is January. Then we go and we march along the year. These are climatologies from 79 to 95. And then so you march along, and then in March and May, you see that little by little the rain belts go to the travel northward. And then eventually it reaches us here. Well, is the most striking feature, of course, are the rainbows that go south and north, back and forth. This is this is the patterns that we meteorologists like a lot, and I hope you like them. They are kind of attractive too. What you see here are these are the arrows that signal how the wind is blowing. And when you see an L here, is that the air is circulating anti-clockwise, right? And then when you have a high or an H, then the air tends to follow these circulations here. So it's everywhere. And this is the boreal. When we're looking at the winter, so we are in the winter hemisphere here. So obviously we have no monsoons. Look, for instance, the granddaddy of the monsoons is the Asian monsoon and the Indian monsoon. And what you see here is how here are the Himalayas. Here the Himalayas are here. This is a big volume of land that will eventually heat up as June comes in summer, and then you will see that this striking feature here will change to this. Can you see the difference? Now it's going north. before it was going, sorry. Before it's going south, right? So this is the mother of all the monsoons is here. So it's amazingly strong. But then we have also the ones in Africa. See, where is it? Here, it's going south too. And also we have monsoon in the southern hemisphere, but these guys are in the summer, right? So in the southern hemisphere we have summers, and so it's the rainy season here. So look at how strongly these things change in Asian monsoon and also in Africa. Remember, it was going the other way. The wind was going the other way around. And now let's look at our monsoon. So here we have what they call, this is a Pacific high and this is an Atlantic high pressure system. And then we have wind blowing to the north. This is our summer. And it's bringing moisture from the Gulf of California and not so much from the Pacific, because the Pacific is very cold. Look at it. Look at this. In winter, we don't have that condition. It's very different. So it's many people have said, "Oh, your Mexican monsoon is not really a monsoon because it lacks the intensity of the other monsoons." But we know it is, because it just suffices to look at the precipitation. Anyways, I'll show you that later. But so we have to have a kind of a conceptual idea of what a monsoon is. And basically, it's a direct circulation. It means that you have to have enough energy coming from the sun. Remember that the atmosphere is kind of transparent to the sun, so it will heat up the surface, and the surface will give off its heat in the form of sensible and latent heat fluxes, and it will eventually warm the column. But to your left, you see what is the Hadley cell. So look at this. There is meridional motion of the parcels, then they will ascend because there is enough energy from the surface to elevate. So there is a lot of instability here. And remember, convection will follow, but also remember that convection and moist convection will tend to homogenize the atmosphere and warm it up. There is a small difference between the quality of the type of clouds that you see in the monsoon, which is to your right. And then it's a more complex circulation, meridional circulation, because it also has shallower type of meridional circulations here depicted in this dotted line. So the thing is, before long time ago, like maybe 30, 40 years ago, we simply thought that these circulations were driven by latent heat flux, by latent heat release from convection. But now we know that it's even more simpler than that. It's simply getting enough energy from the sun and then warm up the surface. That's what drives the circulation, and not the other way up. I mean, it looks very simple, but people were always thinking that latent heat release by condensation would give you everything, but it's not true. And there were many, many papers written about with this idea. So now we know better, we think. So this is the old view. In the old paradigm, monsoons are viewed as circulations driven simply by surface temperature contrast. So the stronger the temperature gradients, the stronger the circulation, and precipitation is just a side effect. In fact, stronger temperature gradients are associated to less precipitation. That was something that was seen in observations. So a new paradigm had to be created, and so the new paradigm included the most obvious thing, that air is moist and can condensate. these models that they had here, most of them were dry air, were for dry air. Well, so that's the way science, progresses. It progresses in tiny little steps. It doesn't really, it's very conservative. We scientists are very conservative. We don't want to change our ideas very quickly, unless there is compelling evidence to do that. Then the new paradigms now are tightly coupled to moist convection. Latent heat release is not what causes large convection. Rather, solar radiation is the main driver. So in this sense, monsoons together with the ITCC, I didn't say what is ITCC. Maybe somebody here knows what is an ITCC. Is intertropical convergence zone, right? Those are the rain belts that I showed you before. Okay. So this is we know now that the ITCC and the monsoons are part of that seasonal migration of the rain bands that occur across the equator. Monsoon circulations help redistribute water vapor and energy globally. It's not just a local thing. It's more than that. And convection in the ascending branch of the Hadley cell and monsoon, they work very fast to homogenize the energy content of the air column. Okay, now let's go to the focus of this talk. And the reason I just explained all that before is because I want you to keep in mind that this is not an isolated phenomenon. It's linked to the rest of the atmospheric circulation. So now, even though I mentioned that this is one of the lesser monsoons that we have in the planet, still is very important. It's important for both Mexico and the US. And that's because from June until September, the Northwest Mexico and Southwest US get more than 70% of the water. So any variability that you see, interannual variability, will affect these people. In particular, it affects the poor, us. So that's the main problem with the monsoon. So we have to be very careful. We know that in Sonora, we are depleting all our wells. They are now the water is saline. You cannot use it for agriculture anymore. And the rest of the northern part of Mexico is also a problem. I had some material to show you, but I thought that maybe we can talk about it later. Okay. Despite being quite different and of lesser intensity compared to their Asian and African counterparts, the NAM shows quite discernible monsoon-like changes in its circulation. I just show you that in the maps. One more thing is that when you focus on this area, what you see here is the color part is the ocean, the temperature, the surface temperature of the ocean. And again, here's just for May, then June, then let's see. Let me see if there is a change in here. June. Oh yes, sorry. It's just the dates that are changing. So I have here the 18th of May, and these are climatologies for the same day. You see, you take the 18th of May of 83, then the one for 84, until you get all the all the May's 18th from 83 to 2010, and then you take a climatology, right? So it's a climatology for that day. And then, why you do that? Because you want to get rid of the noise. So that's then you get a significant signal out of it. And then, so you have an SST here in color, and the isolines here are geopotential heights. They tell you how or how how do you say swollen or yeah. So when the atmosphere is kind of more warm, then it has, see this gradient, it's shallower here and it's larger here, so it has like a tilt. Yeah, it's steeper. Thank you. Yeah, so the gradient tells you about that, and then when you, because this is From theory, you know that this the wind flows along these iso lines of geopotential from west to east. So if you have here what is called a ridge, or in Spanish is called a dorsal, then the tendency is to go around like this. Do you remember how do we call this type of circulation, which is goes with the manecillas del reloj, which is clockwise? Is anticyclonic. So it is a high pressure system. So you have here subsidence, it's very dry here. But then go to this next date in May 28th, and then you see something very remarkable, because now the thing is it's traveling across Mexico. And then on the 8th of June, then it's traveling even forward, northward, and then it kind of settles in the 18th of June. So it goes pretty quick. It travels very fast. And then, well, it intensifies in June and then July. So all of this part gives you, it's 500 millibar or 500 hectopascals. That's 5,000 meters, more or less. That's why you see these labels like 5,000, because it's like that. Okay, so the thing is, the thing is that just to show this is the evolution of the monsoon in Mexico. Eventually, in the lower part of the surface, you have a low, which brings. See how this thing is circulating like this, and this is by the time the monsoon is settled in, this Gulf of California is very hot, so it will give off a lot of moisture, and then if you have this circulation like this, it will bring moisture into the Sierra Madre Occidental, the SMO. The sources of moisture for the monsoon is a very hotly debated topic right now, even for us. My colleague Paulina Ordóñez had to fight a lot of guys to get her paper published, but she did it. Okay, so now the thing is that we can know about the onset by looking at the isochrones of the precipitation. Say you plot everything that is in June 10. Let's see. June. Well, it has to progress. Yes, here's July. So it will progress like this. So the precipitation is going that way. Now look at this. This is the core. Mexico is really the core of the North American monsoon. Are we North America really? I'm not too sure. We should be Mesoamerica, right? I don't know. We have to be different from those guys in the north. I mean, I hate them. Oh, sorry, there is no American here. We are cursed by them, yes. Yes, it's too bad. Okay, so here, my friend Carlos Lizarraga from Sonora, this is his thesis, PhD thesis. And then I want to show you something very remarkable about what happens during the monsoon. It's like a 0 and 1, like a binary type of thing, like a switch. Look at this. This is photographs looking into the same region. This is the dry season, and this is the wet season. Look at the change, a very dramatic change in vegetation. So you would expect then that these guys will evapotranspirate a lot. And also the soil moisture has changed, obviously, because they act like a bank for the soil moisture. They won't give off their moisture just like that. I mean, and then, so you see this, these two are to be compared, and you see that also the effect is striking. My friend, he did some work just to see when the onset is. And these are different places. LH, RA, RY. This is the only one I know because I was here. It's called Rayon. Well, here's Hermosillo and some other places. But anyways, what you see is that there is like a delay in the onset because as I show you, the precipitation is going north, right? So there is a small change in the onset here. But about the peak is in Julian day is like 230, something like that, which is June or July, I mean, yeah, something like that. So, okay, so, and the thing is, as you can see here, it takes just a few weeks to green up. And also, if you look at the entire country, it does the same thing. That's why the core is in Mexico. It's in Oaxaca, it's terribly dry. And then a little bit of rain and poof, that thing. So it's the strategy that vegetation has to survive. It has to go dormant. Okay, so what David Adams and I were working on was in 2013, he brought the idea that he was probably we could use GPS, which is a meteorological GPS. It's not only, you know what GPS are for, right? I think maybe you associate GPSs with just positioning, right? But it does something more than that. And meteorologists are very grateful to the engineers that actually develop all that thing, because you can measure the delay. I will explain shortly how this works. And then we can get very interesting meteorological variables out of it. GPS works with weather station. It has to be just right on its side. I mean, besides it. It has to do, because we need pressure, surface pressure, and temperature data to initialize the calculations. So now investigating the role of vegetation, obviously, so we want to investigate that. So that was the thing that really set us in motion. So our research questions are then, what is the relative importance between the surface forcing and the large scale and mesoscale perturbations in water vapor? So we want to see who brings moisture to the area the most. Is it the vegetation, or is it the large scale circulation? Well, the question, I think, is more or less settled by now. We know that vegetation does a little bit, but it's not, obviously, you can, if you bring in a hurricane into Baja California, then you know that moisture will come from it. So it is the perturbations that are dominant. But still, we want to know how much is vegetation really affecting the precipitation and therefore the deep convection in the region. So we want to design an observational network which includes GPS, meteorological GPS, radio sounds, and flux towers, and isotopes. This is the ideal case. When David and I went to Sonora, we were left with only with GPS and radio sounds and some measure of precipitation. Yes, these things are very costly. So the other thing is that we like numerical models, and this is very interesting because then we can get lots of hypothesis testing with this, and then kind of learn whether some process will dominate or not, or even if the model is completely garbage. So that's something that we need to understand too. I mean, we don't believe in models just because we like them. So now, just to tell you, by the way, how much time I have left. Am I okay? Okay. All right. No. Well, okay. So this is how GPS for the meteorologists work. Here's a satellite. This is a constellation that probably you know a lot more than me. I really don't care too much about this. I care about the result. I'm a user of these things. But I'm told that you even have to know general relativity to understand the tiny little fractions of time that there is delay in the things, because the planet rotates and then the space-time the space-time thing curves or goes around with the rotations. It's crazy, really crazy. But we have to take it into account. So what really is measuring is the delay in the signal from the time the satellite gets to the antenna. It will get delayed by the presence of water vapor. It is quite transparent to all water condensates. It's very interesting. So it's only water vapor that really makes the signal from the GPS antenna to the satellite being delayed. That's very good. So it's noise for the engineers, but it's music to us. And this is more or less because you have to measure the DBZ. Let's see. Yeah, you have to measure this D, which is this is the zenith delay, and I don't know anything else about it. But so I'm here. I want this, and there is all sorts of things going on that engineers know a lot about, and then they give me this, the precipitable water. That is the water that is in the column, and that is capable of being precipitable. It's just water vapor, but it's the integrated measure of water vapor across the column. It's an integral. It's an integral. It's very important because with that we can verify if the models are doing well. This is how they look like, and this is the antenna, just like a regular GPS antenna. But they have to have, as I told you before, a weather station right next to it. Otherwise, we cannot initialize the algorithms. And they have been used for studies of deep convection. And remember always, deep convection transfers mass because it's going up, heat, momentum, water, vapor, liquid in all its phases, water in all its phases, and chemical species and animals, insects and things and everything. So it's very tied to to ecosystems and things like that. So this is our experiment. This is the North American monsoon GPS in 2013. And what we wanted to do at that time was to say something about the transect across the Sierra Madre Occidental, the SMO. So we put several sensors. Well, David did most of the work. I just worked on a few ones. I think Rayon, because it has good restaurants, so I really like them. Nice beef. I'm sorry, I'm a carnivorous guy, and maybe I will switch to other type of proteins later in my life. I'm already quite old, so I should be looking into that very carefully. So the thing is that we needed a contrast here across the mountain range, because earlier experiments did not really look into that. They were more interested in along the mountain range. Okay, so we have 3 transects from east to west. 2. We have also precipitable water vapor measurements from the GPS every 5 minutes. This is very interesting because it's a continuous measurement. Remember that meteorologists have the great limitation of profiling the atmosphere, because every sound launching cost us like 300 USD. It's very expensive. Everyone. So in Mexico, we have like 16 or 13 sites. Every day we launch balloons in order to initialize models and then do forecast, and it's very expensive. And we do it most of the time only in the morning at 6 a.m. For Mexico City, when we have disaster events like the 2 or 3 weeks ago, they start sending more radio zones just to get the models to do a better job. But imagine, this is something that is taking place almost in a continuous manner. That's very good thing. Then we look at precipitation. Okay, this is the distribution in heights of the stations. Is very exaggerated, but just for you to see. This one here is in Chihuahua, is in this is Sonora. I'm not too sure if Cuauhtemoc is part of Sonora or not. Yeah, probably so. But over here is the border between Sonora and Chihuahua. So Chihuahua is here. Cuauhtemoc, Basiceache, Mulatos, Onabas, and Quino. Quino, you know Quino, right? So it's, is it a place for wine or something? I don't remember. But anyways, I've never been there. But the thing is that you design this because you want to see the gradients in precipitation and in precipitable water across the mountain. This is a schematic to help us see conceptually what's going on. It's just a very simple schematic. And we focus on the diurnal cycle of convection in Sonora. So this is the SMO, high peaks, the foothills, and the Gulf of California and coastal plain. It's about 25 north. Hermosillo is at 30 degree north, so this is a bit south of Hermosillo. So what you see in the morning, well, yeah, kind of like in the morning, you see kind of shallow deep convection clouds that develop over the mountain ranges, over the high peaks. And then as convection evolves, see, they have like a cap here, so that's why they kind of open up at higher altitudes. And these tiny little stars means that several microphysical processes are going on inside them, which allow them actually to grow. And these are changes between liquid water and solid hail and snow, for instance. In Mexico, we don't have that much snow, but this is what we call the microphysical processes that are internal to dynamics, or that are linked to the dynamics of the clouds. Okay, so what you see here is like a progression towards the coast. Before it was in the morning was everything located here, because there is something we call anabatic winds, because at 11 hours local time, the mountains have received enough solar energy, and this will give you energy to get moist air. Look at this. This is this shallow layer has lots of humidity that is linked to the Gulf of California. But then you heat up the walls of the mountains, and then the parcels, air parcels, which are moist parcels, will ascend along the mountains, and eventually will condensate, and they don't precipitate right away. They stay there, floating, levitating. And then eventually, as the mountain gives off his heat, they will kind of go towards the coast to get fresher air. And then eventually they reach and then decay. And then this cycle starts again day by day. Well, this is a very useful conceptual model, but is not entirely true, unfortunately. But it doesn't matter, because it gives something to start with, right? I mean, we need something, and then we will disprove it or discard it. Well, it seems that at least from what David and I got at that time, there is something like a progression. This is the integrated precipitable water that I told you about before, the blue line. And the red line is, let me see, yes, it's the cloud top temperature. What is the cloud top temperature? Well, you would imagine that clouds are at the top very cold, right? Very, very cold compared to their surroundings, right? And the more the cloud, the higher the cloud is, the top is colder. So when you have very cold cloud tops, it means that your that your clouds are very cold. And you can see those, you know that information is stored by the satellites. Satellites look at what we call outlong, OLR is outgoing long wave radiation. Because you always emit radiation. Your bodies are emitting radiation, right? If I had a infrared camera, I could see you. Your heads maybe are kind of red because they are thinking a lot, or maybe cool because they are sleeping, or maybe they're already way around. I have no idea. But the thing is that they give off energy in the infrared spectrum. So you have the colder they are, the higher the clouds are. So in here you have the very strong, at the beginning in all of this, you see very strong increase in precipitable water vapor, and then boom, it goes down like that, like this, like this, like this. And you see this in Chihuahua, Cuauhtemoc, Bases, Mulatos, and Onabas. So which one of these is closer to the coast? Onabas, yes. And the one that is on the other side of the mountain range is Chihuahua, right? It's on the other side of the Sierra Madre. So the thing is, if we look at the blue lines here, what we see is kind of like a delay, right? So the bottom here of the blue line is kind of going after. You see, this bottom is going from what is this, 6 p.m. here, around here, and then a little bit later, and kind of recede a little bit. So it's not, our model, our conceptual model is kind of okay, not perfect. But, and what you see here is that when you discharge all your this is the black ones is precipitation. So when you discharge the cloud, it will start raining, and the temperature, the cloud top temperature goes up because it's becoming warmer. So you're destroying the cloud. The cloud is being destroyed there. So that's why you see this behavior. And so it kind of tends to have that appearance that the conceptual model is kind of working. Well, this was made out of, I don't remember how many days, but this is an ensemble or composite of all these measurements during the campaign. So my research question for me and for my colleagues, it's and the paper is still in work in progress. We haven't finished it yet, but the main question is: can a vegetation affect precipitation? Variability at the diurnal, which is, you've seen what is the diurnal cycle of the convection in Sonora, and the intraseasonal scale. By intraseasonal, what I mean is that within a year, within the same year, what will happen between June and October, for instance. So that's what we're looking at. And to do that, we need to separate the effects that large-scale synoptic has on deep convection organization, because large-scale, it has been shown that large-scale synoptic perturbations actually help a lot to organize deep convection in the area. But we want to see if we can separate these guys, which are very large influence, from the little guys, from the vegetation, which causes evaporation, and from the soil as well. So the thing is that we cannot do that in the nature unless we kind of defoliate the entire forest and do something. It will be, maybe we're doing that, right, already. So it will be interesting for us. If we cannot stop that madness, at least we should measure it. What we do in the experiments, in the numerical experiment, is to set the potential evaporation, we call it, set to 0. And then in that case, the vegetation cannot open its stomatal apertures, and then it will just simply stop evaporation from the vegetation. But we also This also controls the evaporation from the ground. So we set it to zero completely. And this is the experiment with a regional model called WRF. These are the domains that we use, so it's a pretty big domain. I think the domain, yeah, this one here is domain 1, this is domain 2, and this is domain 3. Each one of those is like we're focusing on a smaller area, but with higher resolution each time we do it. So it's a nesting type of technique that this type of models use. And it's this model resolves what we call in fluid dynamics the Navier-Stokes equations for moist air. And we use a rather old version because it's very stable. Then we have for each one of these 3 nestings 2.5 for the higher one, which is the innermost domain, and then 10 kilometers for the other one, and 30 for the mother domain. We have 50 vertical levels. Also, it's very important to have enough vertical levels because the Sierra Madre is very steep. So we get, how do we initialize the model? Well, we use initial conditions and boundary conditions from what we call reanalysis. Reanalysis are kind of data, which is not data, but it's model data combined with observations. It's called what meteorologists call an assimilation cycle. So you produce all your radio soundings, your measurements at the surface, and send them to Washington or to someplace in Europe. And then they will start running a model which will give you a gridded, very nice field, which is optimally close to what your observations are giving you. So this is what we call reanalysis. And this, we chose air interim because the Europeans are well ahead of the Americans. American products are not very good now because they have been having bad economic situations like us. So they have lots of cuts from financial to get these things going. So that translates into the quality of the final products. They're very bad in the tropics. Okay, so this is 2012 MODIS. We couldn't use, unfortunately, MODIS at an updated like 2013. We are now willing to look at INEGI type of land use, land cover data. We know that MODIS is the closest, best possible because it matches INEGI a lot. But if you use some other things like the USGS dataset, it's horrible for Mexico. They didn't care, of course. We are Mexicans. It's patio trasero, so there is nothing to do about it. Okay, so we ran the model from July 1st to September 13, and because this covers pretty much the period that we had on our experiment in the GPS. We do also, these are just techniques in order for the model not to become angry at us and spit garbage afterwards. So we have to do several things, but don't worry about those. These are the parametrizations that we need to put. We need parametrization in a model because the grid points that we use are these. This is the best grid resolution in horizontal, but still it cannot resolve all the phenomena. Turbulence, for instance, the flapping of a butterfly won't be resolved by 2.5 kilometers, right? So we need if we want to solve the problem of turbulence, we need to go into millimeters or something like that. It's an open problem in physics, in classical physics. Okay, so what we do is we have the total evaporation, which is divided into, this is from, oh God, let me see. Transpiration via canopy and roots. And this is, sorry because I don't have a picture to show you. It's just picture in your mind, 4-level model in the ground, and with the trees, and the roots of the trees go 1 meter in depth. So the roots will extract moisture and then send it towards the canopy, and then it uses very simple models. They call it resistance models, and so you instead of a tree, what you see is in mathematics is just kind of like a resistance circuit, electric circuit. That's what they use. It's very interesting, actually. For some reason, it has survived this natural selection of all these models. So we have direct E layer is the evaporation from the top soil layer. So we have this, but notice something. Notice that all of these ET, EDIR, EC actually depend on one single factor, EP, which we call the potential evaporation, which is simply the evaporation that we will have if we hadn't any other physical limitation to it, like for instance in vegetation would be stomatal resistance. So all the other terms that are multiplying EP are just part of the physics or the biology that we think is working for the surface. So what we do then is just simply set EP equals to 0 in all the code, and then we shut down evaporation. Just to tell you fast, this is more or less the model, except that it has 4 layers here. Discretized is called the Richards equation, I think, of diffusion. It's a diffusion equation here. It's not nearly as complicated as the ones that we solved for Navier-Stokes, so for the dynamics of the atmosphere. And what we have here is storage of moisture. That's what ds dt, which is the derivative of the storage term, is. If you don't have storage, I mean, if this term is 0, then all that is telling you is that precipitation rates are completely precipitation must plus P minus E minus R RS, which is what's called is runoff, escorrentía in Spanish, and then there is another part which goes into the subsurface flow. I think Graciela knows a lot about this, and probably she thinks this is garbage. But no, she says no. Okay, so I'm happier now. And then, but the thing is that this layer of soil is storing water mass, right? That's the most important thing. I think I made a mistake here. Is this theta dt is the SDT. So please just correct that in your mind. This is just the rate of change of soil moisture here in this part. This one is the energy balance at the surface, which is Rn, which is the net radiation. This is the evaporation, but if you multiply it by latent heat of vaporization, then it becomes an energy term, because you are using your energy, available energy Rn in evaporating. And also SH is the energy that you use to warm up the overlaying air on top of the surface. And then G is a flux term into the ground. So all of these terms tell you what you gain and what you lose. That's all it is to it. There is nothing mysterious. So, but the thing is that the moment you put EP equal to 0, these equations become completely decoupled. And this is something that is not to our advantage, because the moment you do that, then there is nothing to prevent the surface to warm up like crazy, which it did. But it's just an experiment. At least our reviewers didn't say any bad things about it. Okay, so let me show you quickly what we did for that period of time, July. Here on the left, you see precipitation rates. See, I believe this is accumulation in July. So you have, let me see, mean daily rate. Yes, this is, so what you do is accumulate all the rain in the month and then divide by the days of the month. So this is the mean of that rain rate. And this thing is the terrain that for the Sierra Madre. So you see that the precipitation is really concentrated in the peaks of the Sierra Madre. But when you get rid of evaporation, then you see something, right? I mean, like it shrank. So the area that used to be populated by convection, now it kind of, you destroy it. Which was, look at this one, the people didn't like this in Arizona or New Mexico, I think. Then from here, nothing. So, okay, so this is very nice, but does it really tell us what we were looking for? Well, I say just partially, because we still need to look at the diurnal cycle, as I told you, and then this is for other months, so the same effect. So what happens then here is that the total shutoff of evaporation from the surface, it does impact the NAM region. Precipitation decreases in area-wise, and then when you compare the experiment with the control run. And this is something that I wanted to show you. These are results from the model of the same observational data that you saw for the experiment in 2013. So this is what happens for, this is Onabas, Mulatos, Bases and Chihuahua. So this is the eastern part, and this is the west. This is where the Gulf of California is. So the coast is here, and this is where the Sierra Madre Occidental is located. So when you go from, this is west and this is east, okay? So what you see here is again the same type of behavior that you saw before in the observational data. And yes, there is also these black things, is precipitation rates. And well, what we concluded from here, it's very hard to see, but there is some, over here is the experiment. Yeah, this is the experiment where there is no evaporation, and this is the control run. So we couldn't really see that concept, if that thing fits the conceptual model, nor even the observation. So we're still working on it. And so, but at least from the analysis that we did with this and other, this is just one instance. We needed to do a composite, just like the experiment in 2013. What we concluded was that there was indeed some, when you turn off evaporation, then like the convection doesn't evolve at the same rate as in the control. Yes, that's what we saw. But still, the conceptual model is kind of useful. So rates of precipitation diminish when total evaporation from grounds is suppressed. Deep convection propagation towards the Gulf of Coast is reduced significantly whenever. Well, this is something, please take this conclusion with a grain of salt, because we still are working on it. But we wanted to see something really, that's the problem of researchers. Sometimes we want to see what we want. But yeah, it's hard for us to see reality. Then look, what we really saw is that the amplitude of the diurnal cycle in the precipitation is also damped when evaporation is set to 0. I didn't show you all the evidence. In any case, so we have, as future research that is ongoing, to use the model as an Eulerian box, and then compute the hydrological cycle, that is E minus P. Yeah. E minus P is evaporation minus precipitation. I'm going to show you a little bit later how that works. And then run a control run. Well, we have already control run and the experiment. We want to do budget type of calculation to see how, when we turn off the evaporation, the cycle, the intensity of the hydrological cycle changes. And by intensity, I mean evaporation minus precipitation averaged in some sense. For that, we will be running climatologies with a global model, which is MPAS. It's a descendant of the Workshp model, and it has the same dynamical core. And it inherited some of its physical parameterizations. With Workshp, you can choose several distribution of physical parameterizations to fit what you want. So we want to have a regular resolution just to resolve the Gulf of California with realistic and idealized forcings. So this is a hot topic right now, and we want to participate on that. Finally, I know that there is some data as far as paleoclimate is concerned in Sonora, and probably we should use that data and run our models to see if we can fit theories and see if we can advance in the understanding of these very complex phenomena. Since I'm an old guy, I like to write my stuff. It's quicker than using LaTeX, and to write this, it takes me like an hour. So I better do it with my hand, like in the old days. This is just to show you the budget that we want to do. The model has native coordinates. They call eta, and they are ratios of precipitation, of pressure. It's a pressure coordinate system because it goes into in the vertical. And then if you do this thing that you see here is the PWV. The PWV that I show you is the integrated water vapor that is in the column. So you integrate in the vertical, eta is the vertical of the model, and then you get it. So this is what we are going to do, and probably we'll have something. We think that we have something like in a month or two just to get everything computed. This is the integrated water vapor of that run. This is the run on the left and the experiment on the right. Probably you see that it's kind of weird because you don't see that there is a lot of effect on this. You will have to take averages in order to see the actual signal. But in some instances, you see that there are differences between the two. So it has changed. Oh, sorry. Thank you. That's it.
Thank you, Arturo. I would like to request Dr. Muthusankar to come on stage and present a small gift to Arturo. Thank you, Sankar. Thank you, Arturo.